now that we have our best acceleration with error from our data, we want to see how good is it. And one way to do this is to model what this acceleration would bring you. So let's do a x theoretical. And this is going to be in centimeters. So we know that if the initial velocity is 0, that the position based on just acceleration will be equal to 1/2 or 0.5 times the acceleration, and we said our best acceleration was 328 here, times the time squared. And the time here will just be 0. So this would calculate where the car should be with an acceleration of 328 for every time point. So I can fill that down. And now this is my theoretical x. Now I want to make another graph. We don't need these lines anymore. Let's see, this is my x graph. So I'm going to copy this one and I'll make a new one here, paste. And so this one has my original graph with the error of position. And now I want to add on the theoretical graph, theoretical data, and see how well does it fit. So I'm going to select data here. I'm going to add a series. I'm going to call this series x theoretical. The x values here are just time again. And my y values here are going to be my theoretical position. I'm going to say OK. And now when we look at how this is doing, we can see that these orange dots represent where the car would be with 0 initial velocity and a theoretical acceleration of 328. And we can see right there, it matches really well to our actual data. I spelled theoretical wrong, so we should fix that. The nice thing here is we can just fix it up here, theoretical. All right. I don't like the way that looks. All right, theoretical, and maybe I even say x theoretical. Oh, that's good. X theoretical. All right, and then we can see how good it looks here. It's a little bit hard to see, so maybe I'll pick a different than an orange spot to look at this. Go to marker options, and I don't know. Let's think about what we want to put in here instead of a dot. Sometimes a square is nice. Maybe we'll put a square with no fill, and then we can see what's inside it. And then that kind of gives us a sense of where does our point land, except, you know, yeah, maybe not a square, maybe, I don't know, we already used X, we could use a diamond, we could just use a dash too. It's a little hard to see. Maybe if I make it black. Marker, borders, outline, let's make it black. So that maybe it's a little bigger. You can make them a little bigger here if you want with the width. All right, and then now that looks pretty good. I can try see how well does my position land over there, and it looks pretty good bet. We can try real quick to see what would it be with our error. So I could put in our error was 329, I believe. Let's drag this out of the way. So we could go up to 339 and 302. If we put in 339 here for my acceleration and fill it down, now we can see that looks a little bit too big. We're going past our position points. The same way with 302. And we can see that's underneath. So our best acceleration was at 328. And now this really lends some support. Even though we had some uncertainty, let's bring this one to the front, bring to front. We had some uncertainty of velocity. Overall, the best fit line did a really good job of giving us an acceleration that actually models our data and can reproduce what actually happened. That looks pretty good. So this would be a good case, since this matches so well an equation for constant acceleration and matches what actually happened, our data. That's a good argument that that's a good argument that when we look at our graph here of velocity, that it is a constant acceleration, that the line fits this data the best.